Okay, let's begin. So again, I'm going to write on the projector, and if I didn't show it to you, please remind me. And we begin with the continuous time signal, see x of t. And x of t is, in this example, a cos 2 pi ft plus theta. And t is the real number for time. And we plot this. And we remember that a is the amplitude. And the phase shift is theta is 0. And therefore, it looks like what we have here. And of course, if I never give you the capital F for frequency, then you look at here. It took about 1 second, or it takes exactly 1 second to finish one cycle. Therefore, F is 1 cycle per second, 1 hertz. So big F, the signal's frequency is 1 cycle per second. Therefore, it's 2 pi 1t plus theta, the cosine of it. Okay? So this is just a revision. And now we begin to say we have a continuous time signal and we want to sample it. And in this example, I show you that I'm going to sample at 1/8 of a second. That means in 1 second, I'm going to see the value 8 times. So imagine that if the sampler is your eyes and the cosine is running in time, and for example, the cosine is here, and I say open your eyes, and you look at the value here. 1/8 of a second later, which is 0.125 seconds, I ask you to open your eyes again, and you see the value here. 0.125 seconds later, which is 0.25 seconds, the value is here. So you can see that the signal is being sampled at here, at here, at here, at here, at here, and so on. That's okay? So now we have the representation of the signal in this form. X of nts, where ts is the sampling time. So the equation basically go from x of t, which is a continuous time, to a discrete time now, because we are only taking the signal x of t at this time, n of ts, where ts is 1/8, 1/8 of a second. So how do we derive the representation of this equation from this equation? So we just plug a cos 2 pi ft here, ignoring the theta, because in this example theta is 0, no phase shift. T equals nts, so we plug n big T into the small t. So far okay? Clear? And Ts, remember, is 1 over the sampling frequency. Sorry, Fs, the sampling frequency is 1 over Ts. So Ts, we will now represent it as 1 over Fs. So we now get into this equation. Okay? Now, if there's any doubt at all, we'll stop here. Because if we cannot get past this little few equation, then we are going to have lots of problems after that. Okay? So I'll just do it very slowly, and then we'll keep on repeating it. Now, let's observe this equation. So this definitely looks like the previous equation. The A is still there, which is the amplitude. The cosine is still there. That little t becomes n. That's a big change, huge change. On top, that little t is time, continuously. As in, you can use 0.1, 0.01, 0.123, any number you want. Here, n is an integer. You can only use -3, -2, -1, 0, 1, 2, 3, any integers. Nothing in between. And because of this, there is a big change going from continuous time to discrete time. Okay. 2, we don't like to write 2 pi big F over small f. 2 pi big F over big Fs. Instead, later on you will see that I will change this whole thing to small omega. But this represents something. What do you think this represents? So now let's revise first. In the equation on top, you will see that I have written it as x of t, a cosine 2 pi big F of t, ignoring theta first. This whole guy we write as big omega, as in omega is equals to the angular frequency of the cosine. What about the F? What is the F called? The frequency of the signal. We say like 1 Hertz, 2 Hertz, 5 Hertz means 5 cycles a second. Its frequency has the unit cycle per second, or also called Hertz. So okay? What about this guy, which is nothing but 2 pi big F? If F is like, for example, 1 or 2 or 3 or 4, then it's nothing but 2 pi times the number F. That's it. And it has a special name. It is called the angular frequency. And it's called angular because whenever we talk about 2 pi, 4 pi, remember a circle. When you make a circle, you are making how many pi? When I move from here, this point, and I move it to this side, this angle that I have moved is how many pi? 1 pi. And one more time, 2 pi. And one more time, 3 pi and 4 pi. And therefore, if I say my angular frequency is 4 pi, it means in 1 second, I have made how many rounds? 2 rounds, that's all. So the word angular frequency is nothing but the frequency multiplied by 2 pi, because 2 pi represents 1 round. And the word angular here means the angle of your vector, making with respect to the x-axis. That's all. All right, so this is just a revision. And then we come to x. NTS is equals to a cosine. Let us see this. 2 pi big F, the original frequency of the signal, divided by the sampling frequency and n. We can also write it as a cos 2 pi small f n, and we also can write it as a cos small omega n. They all mean the same thing. This is the original equation that you see we have derived. This f is nothing but capital F divided by small fs. It has a special name. Its name is the digital frequency, or sometimes called the normalized frequency. And this guy also has a name. His name is called the digital angular frequency. Okay? So this is all very tedious, but you must get this to your head. And then because we are always going to deal with such kind of signal and such kind of frequency. Let's try to repeat this again. Big omega has a unit radian per what? See, I'm going to have some radian per time, per second. Okay? Radian per second. How many radian I'm going to make in 1 second? What about this guy? I'm going to make some radian. I'm going to turn per sample. That's the unit. Okay? So I'm going to post whatever I've written up here, and then you guys can copy, or you guys can read it along the way.